Welcome to Lecture 8. This week we're going to start and finish talking about a type of mathematics called graph theory. Often when we're analyzing theoretical problems, it's useful to transform the problem into a collection of vertices joined by lines. When he was visiting the city of Konigsberg in 1736, the Swiss mathematician Euler was set a problem by the locals. In order to solve the problem that they set him, he invented a type of mathematics which we call graph theory. The town of Konigsberg, which is now called Kaliningrad, was divided into 4 landmasses by the river. There were 7 bridges between the landmasses as shown in this picture. The problem which visitors to the city were set by the locals is, can a person walk around the town and cross each bridge once and only once? Euler was the first person to solve this problem, and later today I'm going to explain how he solved this problem. If we look at this picture, the important things are where the land masses are and where the bridges are. Or, in fact, we don't even need to know their exact location. We only need to know which bridges connect which land masses together. We don't care about the exact shape of the river. We don't care about where those roads are, where the houses are, etc. We're only interested in which land masses are joined together. If we label the land masses A, B, C, let's say A here, B in the middle, C down the bottom, and then D on the right, we can see that B is connected to D by bridge number 1, D is connected to A by bridge number 2, and so on. The only information we need is given in this diagram on the right. After we learn how to study things like the picture on the right, we will understand how to solve the Konigsberg bridge problem. Graph theory, which was originally used by mathematicians for many years just to solve riddles and puzzles like the Konigsberg bridge problem, is nowadays used in computing, in physics, in neurology, in chemistry, and many other disciplines. Like many types of mathematics, but it started just as an interesting thing to think about or a way to solve problems, but now it has many, many uses. What is a graph? A graph is formed by points, which we call vertices or nodes, and lines, which we call edges. For the vertices, we're going to use lowercase letters, A, B, C, etc. And if we're talking about the edge from vertex U to vertex V, we're going to use the notation round bracket U comma V close bracket. And then we will say that U and V are the endpoints of edge E. A non-empty set of vertices together with a set of edges, which may or may not be empty, is called a graph. If we have an edge which starts and finishes at the same vertex, then we call it a loop. Have a look at this picture. This graph has 3 vertices and it has 4 edges. One of the edges, that's this one, starts and finishes at the same vertex. So this edge is called a loop. For example, let V be the set containing 4 vertices, we'll call them A, B, C, and D, and let E be the set containing 5 edges, we'll call them E1, E2, E3, E4, and E5. And then we're told that E1 is the edge which joins A and B, E2 is the edge which joins B and C, etc. And then the question asks us to draw this graph. The first thing to do is to draw the vertices, A, B, C, and D. And it doesn't matter how we draw them. We could draw them in a square like this, or I could swap some of the points, A, B, C, D. If I wanted to, I could draw them in a line. I could draw them like this if I wanted to. These would all be correct. Just draw the 4 vertices anywhere you want. I'm choosing to draw them as corners of a square. And then we need to start drawing the edges. The first edge joins A and B. So we draw a line from A to B, and we call this E1. The second edge joins B and C. So we draw a line from B to C, and we call this edge E2. And so on. E3 goes from C to D. E4 goes from A to C. And finally, E5 joins B and D. And then we're finished. This is a picture of the graph that we were asked to draw. Two edges with the same endpoints are called parallel edges. A simple graph is a graph without parallel edges or loops. If a graph contains parallel edges, it's called a multigraph. In this graph, in this picture, there are two edges which connect B to C. These are parallel edges. So this is a picture of a multigraph. A pseudograph is a non-simple graph in which both loops and parallel edges are permitted. This is a picture of a pseudograph because it has parallel edges between B and C, and it has a loop connected to A. If E from U to V is an edge of a graph like this, an undirected graph, then the vertices U and V are called neighbors in G. The degree of a vertex in a graph like this is the number of edges connected to that vertex. When we're calculating the degree of a vertex, we count a loop as 2. So, for example, give the degrees of all of the vertices in graph G. So we have 7 vertices, A, B, C, D, E, F, and G, and we need to count the number of edges connected to each vertex. First of all, let's look at A. We can count 1, 2. So the degree of A must be 2. Next, look at B. How many edges are connected to B? 1, 2, 3, 4. So the degree of B is 4. The degree of C is also 4 because there's 4 edges connected to it. Vertex D has got only 1 edge connected to it. So the degree of D is 1. And so on. The degree of E is 3. The degree of F is 4. And G doesn't have any edges. So the degree of G is 0. Let's do another one. Here's a graph which I'm calling graph H. Give the degrees of all of the vertices in graph H. This time we've got 5 vertices, and for each vertex we need to count the number of edges. At A, 1, 2, 3. At B, remembering we're counting a loop as 2. So 1, 2, and then keep going, 3, 4, 5, 6. The degree of B is 6. The degree of C is 1. The degree of D is 5, and the degree of E is also 5. A vertex which does not have an edge, so in other words, a vertex which has degree equal to 0, is called an isolated vertex. In this picture, vertex G. In this graph, vertex G is an isolated vertex. A vertex of degree 1 is called a pendant. A pendant is a vertex which has only one edge. In this graph, vertex D is a pendant. And then we come to the first theorem of today's lesson. Let G be a pseudograph. That's a graph in which we're allowed to have parallel edges and we're allowed to have loops. And let N of E denote the number of edges in G. Then the number of edges in G is a half multiplied by the sum of all of the degrees. So for example, if we go back to, let's say, this graph, if we add all of the degrees together, 3 plus 6 plus 1 plus 5 plus 5, that's 20, and then divide it by 2, we should get the number of edges. This graph should have 10 edges in it. So let's count them. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. The number of edges in a graph is always a half multiplied by the sum of the degrees of the vertices. For example, a graph has 10 vertices and each vertex has degree 4. How many edges does this graph have? Well, we have our theorem. We're going to do a half multiplied by the sum of the degrees. So it's a half degree of vertex 1 plus degree of vertex 2, etc. But we're told all of these are 4. So it's a half multiplied by 4 plus 4 plus 4 plus 4, etc. A half of 40 is 20. So we know that this graph must have 20 edges. So far, we've been talking about undirected graphs, graphs where all of the edges do not have a direction. But sometimes you might want to be looking at a graph where the edges do have directions. This type of graph is called a directed graph or a digraph. The direction tells us where the connection starts and when it finishes. If a directed graph has parallel edges, then it's called a directed multigraph or a multi-digraph. This graph, for example, has parallel edges, so this is a multi-digraph. Let me just remark that in a graph, all of the edges are the same type. So either all of the edges are directed or all of the edges are undirected. We don't mix them together. Let G be a directed graph. Now, when we write E is equal to open bracket U comma V close bracket, now the order of U and V is important. This tells us that the edge starts at U and it finishes at V. We can also talk about degrees of vertices in a directed graph, but we have two different types. We have an in degree. That means the number of edges coming into V, and we also have an out degree. That means the number of edges which are coming out of V. When we count in degrees and out degrees, a loop is counted as 1 for both in degree and 1 for out degree. For example, find the in degree and the out degree of each vertex in the graph drawn here. First, let's look at the in degrees. We need to count the number of arrows which point towards a vertex. A has 1, 2 arrows pointing to it, so the in degree of A must be 2. Vertex B, how many arrows point at B? 1, 2. The in degree of B is also 2. C, 1, 2, 3 arrows pointing towards C, so the in degree of C is 3, and so on. The in degree of D is 2, the in degree of E is 3, and the in degree of F is 0. And then next we want to count the out degrees. How many arrows are coming out of A? 1, 2, 3, 4. The out degree of A is 4. How many arrows are coming out of B? Just 1. How many arrows are coming out of C? 1, 2. The out degree of D is 2. The out degree of E is 3, and the out degree of F is 0. What do we get if we add these numbers together? First of all, 2 plus 2 plus 2 plus 3 plus 3 is 12. And if we add the out degrees together, 4 plus 1 plus 2 plus 2 plus 3 is also 12. And that is the number of edges in this graph. Let's write that as a theorem. Let G be a directed graph and let NE be the number of edges in G. Then the number of edges in G is the sum of the in degrees, and it's also equal to the sum of the out degrees. A simple graph which includes all possible edges is called a complete graph. Remember, simple graph means we're not allowed to have parallel edges and we're not allowed to have loops. So all possible edges means that every vertex is connected to every other vertex. In a complete graph, every vertex has an edge, one edge, which with every other vertex. A complete graph which has n vertices is denoted by Kn. And I'm going to show you pictures of the first few complete graphs in a moment. The degree of every vertex in Kn is n minus 1 because there's n vertices, so each vertex is connected to the other n minus 1 vertices. And that means that Kn has n multiplied by n minus 1 divided by 2 edges. Add all of the degrees together and divide it by 2, we get the number of edges. So here they are. K1, the complete graph with one vertex, has 0 edges. K2, 2 vertices and 1 edge. K3, 3 vertices and each vertex is connected to the other 2. K4, K5 and K6. A planar graph is a graph which can be drawn on the plane in such a way that its edges intersect only at their endpoints. So for example, this graph, you can see the edges are crossing over, they're intersecting here. But this is still a planar graph because we can draw this graph in a different way. If we move the vertices around and move the edges around, we can draw it like this. I'll leave it for you to check this is exactly the same graph. For example, A is connected to B, A is connected to B, A is connected to D, A is connected to D, A is connected to E, A is connected to E. All of the edges are the same. But in the right-hand picture, the edges do not cross each other. So this is a planar graph. Sometimes that's not possible. A graph that is not a planar graph, that means it can only, we can't draw it in two-dimensional space without intersecting edges. We can only draw it in 3-dimensional space. It's called a 3-dimensional graph. For example, this is a 3-dimensional graph. I've tried to show that these crossing edges are not on the same level. You're going to think of one of these as being higher up or closer towards you than the other one. And I'll leave it for you to look at this and convince yourself that it's not possible to rearrange the vertices and the edges of this graph so that the edges do not cross each other. Suppose that n is a natural number which is 3 or bigger. Let V be the set of n vertices and let E be the set containing these edges. V1 is connected to V2, V2 is connected to V3, V3 is connected to V4, V4 is connected to V5, etc. And then the final edge connects the last vertex with the first one. Vn is connected to V1. This type of graph is called a cycle graph, and it looks like these. We call these Cn. This is C3, the cycle graph with 3 vertices, then C4, then C5, then C6, etc. If we take Cn and we add a new vertex, which is attached to all of the other vertices, then we get a type of graph which we call a wheel graph, Wn. So take Cn and add another vertex in the middle and then connect that vertex to all of the other ones. We get W3, W4, W5, W6, etc. And let me just note that now the number doesn't tell us how many vertices we have, because W3 has 4 vertices. So why are we writing it like this? Because it's based on C3. We started with C3 and then we added one more vertex. Likewise, W6, we started with C6 and then we added one more vertex. So it's always 6 plus 1 or 7 vertices. A bipartite graph is a graph where the set of vertices can be divided into 2 distinct subsets, V1 and V2, such that every edge connects a vertex in V1 with a vertex in V2. We say that another way. In a bipartite graph, there are no edges going from V1 to V1, and there are no edges going from V2 to V2. So for example, the graph C6, last time I drew this as a hexagon. But we don't have to draw it like that. We can move the vertices and the edges around however we want, as long as the same vertices are connected together. If we draw it this way, we can see that the 3 vertices on the left are connected to the 3 vertices on the right. Every edge goes from the left to the right. There's no edge joining 2 vertices in V1, and there's no edge which joins 2 vertices in V2. Here's a graph. Is this graph a bipartite graph? How can we decide if this is a bipartite graph? We can decide it by coloring in the vertices. We need 2 different colors, any 2 colors. Let's say I have an orange pen and a green pen. I'm going to pick one of my 2 pens, and I'm going to use that to color in one of the vertices. So pick one color, it doesn't matter which one, and pick one vertex to start with. It doesn't matter where you start with. Let's suppose I pick my orange pen, and let's say I'm going to start at B. I'm going to color in B orange. And then after I've done that, I'm going to change to my other pen. Next, I'm going to use my green pen, and I'm going to color in every vertex which is connected to B. So for example, C is connected to B, so I'm coloring this one in green. E is connected to B, I'll color that one in green, and F is also connected to B. I'm going to color that one in green. Now let's just do a quick check. Are there any green vertices connected together? The answer is no. C is not connected to E, C is not connected to F, and E is not connected to F. So far, good. Put the green pen down and pick the orange pen back up. I want to color in every vertex which is connected to a green vertex. So here we go. A is connected to a green vertex, and D is connected to a green vertex. And quickly check, do we have an orange vertex connected to an orange vertex? No. Good. Go back to the green pen. There's one vertex left. Let's color that one in green. So now we have A, B, and D colored orange. C, E, F, and G are colored green. The orange vertices are not connected together, and the green vertices are not connected together. So that tells us that we have a bipartite graph. To see this further, we could draw this graph another way. We could draw all of the orange vertices on the left, and we put all the green ones on the right, and then we're going to have to draw exactly the same edges that we had before. I'll leave it for you to check when you have time. This graph is exactly the same as the previous graph. All of the edges are exactly the same. A is connected to the same vertices, B is connected to the same vertices, etc. It's now easy to see that every edge goes from orange to green. Let's do another one. Look at this graph. Is this graph a bipartite graph? Well, we do the same method. We'll take our green pen and our orange pen, and we'll start coloring in. We can start anywhere we want. Let's say I start with my green pen, and let's say I start with D. I'm going to color D in green, and then I'm going to change to my orange pen, and I'm going to color in every vertex connected to D. And then we need to do our check. Are there any orange vertices which are connected together? Yes. E is connected to F, and both of them are colored in orange. That tells us that this graph is not bipartite. Let's change topic. And the next important idea in graph theory is the idea of walks. What is a walk? A walk is a list of vertices and edges, and it's in the particular order it goes: vertex, edge, vertex, edge, vertex, edge. And it's written in such a way that each edge is the edge which connects the vertices it's between. E1, for example, is the edge which connects V0 to V1. So, for example, let's suppose we started at vertex A, and from A we walk to B, and then from B we walk to E. From E we walk to D, and then from D we walk to C, we walk to F, we walk to G, and then we walk back to F. We could write this as a list of vertices and edges. We're starting at A, so we write A first. We use edge E1 to get to B. So next in the list, we write E1B. We use edge E1 to travel to B. And then we go from B to E. So we write E5, we use an edge E5, and that takes us to E, and so on. This is a walk in this graph. An Eulerian trail is a special type of walk which satisfies two rules. Rule number one, no edge is repeated. We can only use each edge once in our walk. And rule number two, we have to use every edge in our walk. For example, I'm saying the walk, which I've written here, starts D, E5, E, E6, A, etc., is an Eulerian trail, because each of the 10 edges appears once and only once in this list. Let's check this. So what we're doing, we're going to start at D, and we're going to take E5 to get to E, and then we're going to go to A, and then we're going to go to F, and from F to B, from B back to A, from A to D, from D to C, from C to G, from G to B, and from B to C. We've used every edge once and only once. So this is an Eulerian trail. And that brings us back to the Konigsberg bridge problem. The Konigsberg bridge problem was, can a person walk around Konigsberg and cross each bridge once and only once? But that could be rephrased as, does there exist an Eulerian trail in Konigsberg? We'll be answering this problem soon. First, we need some more theory. A graph is connected if there exists a walk between every pair of vertices. So, for example, in these pictures, graph H is connected. Pick any two vertices. Let's say I pick C and E. It's possible to walk from C to E. Graph G is not connected because it's not possible to walk from G to A. Now we have our theorem. Let G be a connected graph. Then there exists an Eulerian trail if and only if the number of vertices of odd degree is either 0 or 2. So there's either no vertices which have odd degree, in other words, every vertex has even number degree, or two of the vertices have odd degree and the degree of every other vertex is an even number. And then the theorem goes on, it says, furthermore, if G has two vertices of odd degree, then the Eulerian trail must start and finish at these two vertices. Let's look at the complete graphs. In K3, first of all, the degree of every vertex is 2. Every vertex has an even degree, so that means there exists an Eulerian trail in K3. Likewise, if we look at K5, if we count the degree of every vertex, they're always 4. Even number, even number, even number, even number, even number. So the theorem says there exists an Eulerian trail in K5. But there does not exist an Eulerian trail in K4, because if we count the degrees, degree 3, degree 3, degree 3, degree 3, all 4 vertices have an odd degree. So by the theorem, there does not exist an Eulerian trail in K4. And this one, which we looked at earlier, the degree of A is 4, the degree of B is 4, the degree of C is 3, degree D is 3, degree E is 2, degree F is 2, and degree G is 2. There are 2 vertices which have odd degree, and all of the other vertices have even degree. The theorem says there exists an Eulerian trail in this graph, and it must start and end at C and D. And actually, we've already found this trail. We've already seen that we start at either C or D, and we finish at the other one. Now we're ready to answer the Konigsberg bridge problem. Does there exist an Eulerian trail in Konigsberg? To answer that, we need to count the degrees of each vertex. The degree of A is 3, the degree of B is 5, the degree of C is 3, and the degree of D is also 3. So we have odd number, odd number, odd number, and odd number. We have 4 odd numbers, so by the theorem, there does not exist an Eulerian trail in Konigsberg. So the answer to the problem that Euler was the first person to solve is it's not possible to walk around the city of Konigsberg and cross each bridge once. Let's change topic. For the rest of today's lesson, I want to talk about Euler's formula for polyhedra. Euler's formula for a polyhedra is the number of vertices minus the number of edges plus the number of faces. Let's look at a few simple three-dimensional objects. I want to count the number of vertices, number of edges, number of faces, and then I want to calculate Euler's formula for each one. A cube, how many vertices? We can count them. 1, 2, 3, 4 on the top, and then another 4 on the bottom, so that's 8 vertices. How many edges? 1, 2, 3, 4 on the top. Vertical ones, 5, 6, 7, 8, and then another 4 on the bottom. Those must be 12 edges. And how many faces on a cube? Everybody knows a cube has 6 faces. And then Euler's formula is number of vertices minus number of edges plus number of faces. So 8 minus 12 plus 6. And for a cube, we get 2. Okay, let's do another one. What about a tetrahedron? A tetrahedron has 4 vertices. Each vertex is connected to another 3 vertices, so 4 multiplied by 3, and then divide by 2 so we don't count each one twice. 4 multiplied by 3 divided by 2 is 6. That's the degree of all of the vertices, add them together, and then divide by 2. And a tetrahedron has 4 faces. Euler's formula is then 4 minus 6 plus 4, which is 2 again. Is that a coincidence? Let's keep going. A pyramid. A pyramid has 5 vertices. It has 8 edges, count them, and it has 5 faces. So if we do Euler's formula, 5 minus 8 plus 5, which is 2 again. That's strange. Let's keep going on. Is it always going to be 2? A dodecahedron, a 12-sided shape, where each face is a pentagon. There's 20 vertices here, 30 edges, and 12 faces. Let's do Euler's formula. 20 minus 30 plus 12 is, that's 2 again. Let's take another shape. Let's make a bigger one and see if we can get a number which is not 2. Let's look at this shape which I'm calling a football. We have 12 pentagons and 20 hexagons. Okay, 32 faces. 12 plus 20 is 32. How many vertices? Well, every vertex is on a pentagon. So we could do number of pentagons and then multiply it by 5. 12 multiplied by 5 is 60. And how many edges? We have 60 vertices. Every vertex is connected to 3 different, has 3 different edges. So 60 multiplied by 3. And then we divide by 2. 60 multiplied by 3 is 180. Divided by 2, we get 90. There must be 90 edges here. And what do we get if we do Euler's formula? 60 minus 90 plus 32 is 2. We're always seen to be getting 2. If we have a polyhedron without any holes in it, is Euler's formula always going to be equal to 2? Now, when I say a polyhedron without any holes in it, I'm not interested in things like this. I don't want some sort of solid shape which has, that we can stick our finger through and it comes out the other way. I only want a polyhedron which doesn't have any holes in it. And I want to answer the question, is Euler's formula always going to be equal to 2? And If we think it is, how can we prove that it's always equal to 2? And why are we talking about this in a lecture about graph theory? Let's go back to looking at the cube, and I want to think of it like this. I want to take the cube and I want to remove its top. Now I'm going to throw the top away, and then I'm going to start stretching and squashing the cube. So far, the number of vertices is the same, that hasn't changed. The number of edges is the same, that hasn't changed. But because we've thrown away the top of the cube, the number of faces has decreased by 1. Let's squash this flat. Same number of vertices, same number of edges, but we've got 1 less face. In order to account for the face that we threw away, I want to count the outside of this. I have a graph here which has 8 vertices, same as the cube. My graph has 12 edges, same as the cube. And if we count the regions which are enclosed by edges, 1, 2, 3, 4, 5, 6, and if we count the outside as 1, because we threw the top of the cube away, we get 6 faces. I could do the same thing with a tetrahedron. Take one of the faces off and throw it away, and then squash your tetrahedron flat. We still have 4 vertices, we still have 6 edges, and if we count the outside as the missing face, we still have 4 faces. We could do for a pyramid, 5 vertices, 8 edges, 5 faces. Or if we had some sort of 3-dimensional object like this capital T, again, take one of the faces off, throw it away, squash it flat, we would have a graph like this. Both the 3-dimensional object and the graph have 16 vertices, 24 edges, and 10 faces. The idea here is that every 3-dimensional polyhedron, which doesn't have any holes in, is equivalent to a connected planar simple graph. So if we know something about these graphs, then we also know that it's true about polyhedron. So what do we know about graphs like this? This is a key idea in mathematics. If we try to solve a problem, we might find it's easier to convert it into a different type of problem, solve the different type of problem, and then go back to and find the solution of the original problem. Instead of thinking about 3-dimensional objects, we're going to be thinking about graph theory. If we can solve a problem in graph theory, then we also know that the thing is true for 3-dimensional objects. Let's start with the first complete graph, K1. This graph has got 1 vertex, 0 edges, and 1 face. If we do Euler's formula for K1, we get 1 minus 0 plus 1 is 2. So Euler's formula is equal to 2 for K1. Next, let's take any connected planar simple graph. So that's any graph which does not have loops and does not have parallel edges, which we can draw in a 2-dimensional plane without any of the edges crossing each other, and such that there exists a walk between any 2 vertices. So it's something like this. Just draw anything you can imagine. And then what can we do to simplify this? Well, one thing we could do is we could cut off a pendant. What happens if I cut where the scissors are? Well, we're going to be removing one edge, and we're going to be removing one vertex. So the number of vertices is going to decrease by 1. The number of edges is also going to decrease by 1. The number of faces is going to stay the same. We haven't changed that. So number of edges is -1, and then minus. Number of edges is also -1, and number of faces stays the same. So -1 minus -1 plus 0. -1 plus 1 is 0. That means if we remove a pendant vertex like this, Euler's formula does not change. It stays as the same number. What else can we do to simplify a graph like this? We could cut an edge which is not connected to a pendant vertex. And then what happens if we do that? The number of vertices is not going to change if we remove this edge. NV is going to stay the same. I've removed an edge which used to be there, so the number of edges decreases by 1. And we used to have 2 different faces, but now they're joined together. So the number of faces is going to decrease by 1. But that means Euler's formula stays the same. 0 minus -1 plus -1 is 0. If we remove an edge like this, then Euler's formula is not going to change. And then we can carry on. Here's another pendant vertex. We can cut this off, and Euler's formula doesn't change. And then keep going. Keep simplifying it using these 2 operations. Every time we do this, Euler's formula doesn't change. And then what we're going to get left with? We're going to get left with K1. We're left with 1 vertex, 0 edges, and 1 face. So we're left with Euler's formula is equal to 2. But every time we simplified this, we didn't change Euler's formula. So that means that the complicated graph that we started with also has Euler's formula equal to 2. We can say that every connected planar simple graph has Euler's formula equal to 2. And if we know that that is true for connected planar simple graphs, then we also know that's true for polyhedra without holes. Every polyhedra which does not have a hole in it has Euler's formula equal to 2. And that is the end of this week's lesson. Next week, we change topic again. We're going to start talking about calculus. I'm going to cover the chapters limits, continuity, and differentiation. Are there any questions?